Swayam Prabha. Digital India. Educated India.
Can go. All right, welcome back. So this is actually a very important slide. Lots of terms that you'll hear over and over again. So we've looked at the definition of ductility, but the way ductility is defined. So in this case, you see that if you have any structure, and let's say this is again, most of my references will be based on a simple, let's say this is a load versus deflection, whatever be the type of load. It's not necessarily dependent on the type of load. So if the response is something like this, and then you have your behavior, again it is on response of the structure. You can also predict these responses, so whether it is experimental or predicted, either way. So you have this, we will call is delta yield, and this is the maximum that it can withstand. So here we will use the ductility as mu, which is delta max divided by delta yield. So that's a definition of ductility ratio and you can have this for even concrete structures. You can have this for masonry type structures also, although the ductility ratio, as I said earlier on, concrete, masonry, they don't have a well defined maximum deflection, right. So in those cases then we go into support rotation, which we will come later on, which will address. The next is impulse. You will see that this is the loading. Most, even if you see wind, is time a factor in the wind loading? Do you consider time of loading as a wind? You don't, right? But in this case, the time is an important element in a couple of different ways. So this is the pressure, say maybe in kilopascals, or and then the time, and you will see the time scale is also quite different. The time scale will be in milliseconds. Wind, earthquake, seismic loading is dynamic, but that time frame is more in order of minutes, or maybe a minute, whatever, seconds even. But here the order of loading itself is in milliseconds. So as we will describe the loading, it's not quite like this, there are varieties, but if it is in this way, the impulse is nothing but integral of P dt. So this is the impulse. The area under this is what you will see as an important, or the pressure time history. Then we have already talked about this, the level of protection. There are multiple levels of protections. The desired, again this is in a way not the seismic definitions of protection performance based design, PBDs, but this is the desired performance designated for a building based on use, and that is a part of our afternoon example as well as your tutorial. And owner needs. We will, at least from our engineering perspective, define what the threat is, and that threat is based on that you can go with levels of protection. Then hinge mechanism. This is very standard, as you see in all steel structures, even concrete structures. You can have formation of a plastic hinge. I think this is something all of you would be quite familiar with. Then you have response limits. So just like serviceability criteria, you have delta dead load should be less than the span divided by, I don't know, at least in the US we use dead load plus live load is L over 240, or delta live load is less than L over 360. In this case, the response limits is the actual rotation or ductility. The support rotation, as I am coming to it later, but let me give it, we will call it theta, and the ductility is mu. Mu would be applicable especially for steel type of structures. Theta would be more applicable for concrete type of structures. We have seen what the standoff distance is. That picture did not come out very well. All buildings, as you will see, let us say this is your building and this is your explosive. The standoff threat distance is the perpendicular distance between your explosive and the building, and of course that is how you design it, but the building has different heights, and so you can have what is known as the angle of incidence. So this angle is, I have not defined it here, but this is, let us say, the angle of incidence, and then your standoff distance is r. So there is a distinction that is drawn. Your baseline is standoff distance, and your angle of incidence is a part of, if you want to, pressures keep decreasing as you go up anyway. The peak pressures are at the shortest r value. Then you have support rotations. I have defined it earlier on, the peak deflection of the component normalized to the distance from the support, that is, we talked about your theta being approximately equal to delta divided by L over 2 irrespective of the type of loading. And yield deflection we have talked about there, corresponding to the formation of a mechanism. So it is not necessarily when the material first yields, it is not material yielding that comes into play out here. So this is the plastic hinge formation, that is what we look at. So we are going to do more about it, especially today is focused, a lot of focus is on risk assessment. One of the first things that is done in a design is risk assessment. First of all, is even a design for blast necessary? And to me, I have been working, as I was talking a little earlier during the break, some people do not include risk assessment as a part of it is actually the course that is not offered, even in the US it is not, maybe a few universities offer it, I do not know of any myself, but so some of them, if they do offer risk assessment, could be or could not be a part of it, but focusing from a practical perspective, since the students we have are both engineers as well as regular graduate students and undergraduate students. So for me, risk assessment is a big part of what you do in a design. So the approach varies in general, includes several things. Occupants, will go through the UFC that is there for it. Then you have the assets. Assets I had mentioned earlier, equipment that are stored in that building. The type, if it is a hospital, where is the radiation room? Because in an emergency situation you want that to be functional. Where are the MRI rooms situated? MRI rooms I have seen are designed for blast resistance. If you see, even if a structure is not fully designed for, but they do take care, if it is a critical facility, then they do take care to design at least those structures to shield both for radiation as well as blast effects. So location of it. Then we do a threat analysis, and from the threat analysis we will go through this in the next, you will see what are all the different things, steps that are involved. The type of threat. So when we talk of the type of threat in terms of TNT weight, the type, whether it is TNT or it is another type of explosives, or it is what is known as ammonium nitrate fuel oil. These are different types of explosives, what is a potential aggressor going to use is a consideration depending on the facility that you are designing for. The size of it, so this comes to the weight of the threat and the location. This is basically the standoff distances or even where it is situated. Then based on all this, so we do, this is a threat analysis. Then we conduct in the risk assessment a vulnerability assessment of the structure. So this is irrespective of the threat, how vulnerable is the structure. So there is an assessment process for that. Sensitivity of the assets, so that is the second thing. And then finally, so if you see it's based on three things: assets, threat and vulnerability. So this is 1 here, 2 and 3, and all of this combines into a risk analysis. But before we get to that, there are a lot of other things to look at. So these are levels of protection are classified under what are known as performance expectations. These are called LOPs. So as you beginning to see the distinction, the first thing is defining the threat, then vulnerability comes into play. So that's where this is, the LOPs is a part of the vulnerability assessment of the structure. It's of the risk analysis part. So there are, how is it classified? Just like in seismic, you can't have too many categories. It's quite broad based, and one person can do a different analysis compared to the other. So there is subjectivity involved in this. So you have low or medium LOP. So we call this LLOP or MLOP. So this is major damage. So when you have a low level of protection, which basically you can expect a much higher damage. So there is a major damage to the building. Then medium LOP is moderate damage and it is repairable, and then you have a high LOP which is repairable and there is very minor damage. So this is of course much more costly, cost considerations definitely. So as you see, this is go this way, you have increasing cost considerations. So this is the document from the UFC 410-01. You have various, for new and existing buildings, as you see, this is levels of protection below 80 is anti-terrorism standards, and it defines the building damage, performance, what can be expected from very low. There is also a very low category, low, medium. So you have here VLOP, LOP, and these are distinct. So and so there is a broad basket classification of what you can expect. For example, in high LOP, only superficial injury is likely, whereas in low LOPs, majority of the personal damage suffer minor to moderate injuries. So being familiar with this is important. If you see a low LOP doesn't mean the building or the personnel inside are not. Here if you see the damaged area suffer minor to moderate injuries with potential for few serious, but fatalities are unlikely. So this is LLOP. So this and here of course below 80 standards. So even in the lowest you have this is very low protections. Majority of the personnel suffer serious injuries with the potential for fatalities. In areas outside the damaged area will experience. So in the vicinity which experience the peak, you can expect fatalities. Outside of it, probably not. So be familiar with what is contained in some of these charts. So what are the overall analysis and design steps? Defining the parameters, threat, basically the size, W, and location. R is the standoff distance. So those are the two things. This is what is known as the design basis threat, DBT, as I had mentioned earlier. Then based on the DBT, once you have these two, then we'll cover all these in this over the next few days. We define the loading based on the threat. Once you have W and R, how do you define a pressure time curve for it, and how do you translate to buildings as well? I know one of you mentioned you're a mechanical engineer, and a lot of these are design basis, so we have to convert what you see physics wise into civil engineering type applications. Although thank you for mentioning, I'll see how I can focus a little more on that side as well. Then once you have the loading, modeling of the structure elements as single degree of SDOF models. This is also something we will be covering. We will go through all these steps perhaps in the first week, or maybe into Monday as well. Then defining material behavior. This aspect is not very detailed, although if you go through some advanced analysis, this can be the most challenging aspect of it. The material model development, if some of you have done PhDs, and I mean my whole PhD was to develop a constitutive model applied in finite elements for metal matrix composites with cyclic plasticity behavior. So we can, I mean, I don't think I even cover the topic fully in one PhD. I did it over 5 years. So material modeling can get into multiple courses. You have to do elastic, plastic, plasticity, continuum mechanics, all those things put together, and then experiments. Then you do have, as you know, a model is only as good as the parameters and how well you can measure the parameters experimentally, right? So those of you with that experience know it is the most challenging aspect of it. For example, one of the models I know for concrete has about, I don't know, 28, 30 plus parameters, and it's used quite widely. How do you even, you can measure, you can do a tension test, you can do a couple of parameters there, you can do a couple of other tests, and somehow, and all those parameters are restricted to the conditions of the experiments you perform. At the end of the day, you don't, but what we are doing is extrapolating. Those parameters are good for interpolating, but when you start extrapolating, you're on your own, right? So although it can be one of the most challenging aspects of it, but for this course we'll keep it quite simple. Designers love to do that. And then determining the response, and this can be, as I said, either from an advanced analysis, either using a SDOF solutions program, or performing advanced analysis. When I say advanced analysis, of course you're using finite element methods, and and then you're defining a force deflection response. So this is from established design principles. You have to ultimately translate what we are putting forward into something a designer can use in a simple manner, he or she. So you define that from either experiments. People do a lot of experiments on walls. Again, funding in this area is very, very competitive and limited too. Not everybody wants to do a lot of things unless it is really applicable to them. So given those challenges, defining a force deflection response can be at best predictive based on the principles that we know already, and then comparing them with the allowable values based on the LOPs. The LOPs that we talked about a little bit earlier, they convert into support rotations. So the LOPs gets translated to theta and mu values. We will spend quite a bit of time in determining the response. These responses are both based on elastic behavior. This is the simplest. The programs we can use are assume a certain elastic and don't incorporate, simple programs don't incorporate plasticity models. But we will also see how to translate it into elastoplastic behavior. So I think in all of this it's good to consider, and once again a disclaimer, I am not a explosives person. I collaborate in fact with a person who works in mining engineering, and all they do is study the physics of explosions under whatever conditions. But given that in this area you need to know at least some basics. Physical are CNG cylinders, of course, that we know. In fact, we will see later on that the progressive collapse in fact began from a cylinder, LPG cylinder blast, not CNG, that was an LPG cylinder, and it collapsed an entire building, multi-story building. It happened at, I don't know, some floor well above, and then you can see how the collapse. So that is something that led to progressive collapse. We'll look at that later on. So that is either cylinders or violent mixture of, and some of the most, this is ammonium, I hope I've spelled it right, nitrate fuel oil. Why is this most common? Any guesses? Mining, more common, not mining is not so common. Fertilizers, right? A lot of these chemicals are available for use as fertilizers, not in the same combination, of course, but ammonium nitrate, right? You use it as fertilizers, so it can easily be converted to explosives. Don't Google about finding how to do it, you might be in trouble. Nuclear explosions, this is not in this course. We will not even touch on that particular topic. There, in designing nuclear structures for impact, nuclear structures are primarily designed a lot more for impact more than blast, because aircraft, that's a real danger, right? Anytime if aircraft impacts it. What's the biggest design consideration for nuclear structures? Or how do I put this? Maybe the question is not, if you were designing a nuclear structure against an aircraft impact, what would be your primary design criteria? No crack, is it? Yeah, okay. For that, what type of design would you have to do? Elastic behavior, right? So your entire structure is completely elastic. So which means dams often are fully elastic behavior, very thick structures, right? So the design philosophy is very different there. So that is not what we will cover here. Chemical reactions, this is a lot of petrochemical facilities. In fact, if some of you are interested in that area in the future, ASCE has a whole book on some of the designs of these. Again, this is a dated book. I don't know if they're going to update that, but at least there is a document I have. I bought some copies. Maybe in the afternoon I'll bring ASCE and a couple of these books also and show you. So this is rapid oxidation of fuel elements forming part of a explosive. Oxygen is needed as a part of the component of the compound. So explosion creates, there are two types, either an explosive cloud and or I should say a blast wave. So it's basically again detonation, a lot of it whether it's a charged shaped, it's in contained detonation or it's an open detonation. If it is contained, then you have fragmentation of the containment structure, and then that also can cause impact. So we've worked with IIT Dhanbad, who was a PhD student. We worked and we published 3 papers on that, fragmentation, effects of fragmentation and blast. So what happens when you do impact there is it reduces the stiffness of the structure. The number, you have to not only account for the pressure time curve that is purely for blast, but you have to estimate, okay, I have a cylinder made up of steel and this is the size, and then how many fragments, you have to estimate the fragments. You have to estimate the velocities of the fragments. It's really no way to accurately do all those things, but what is the right estimate, and then how it impacts, what velocity it starts, what it impacts with, what that impact causes, what damage it causes, reduces stiffness, how much does it reduce the stiffness, as a reduction, which one comes first, does the fragments come first or the pressure comes first, that matters, right. So you're already in a blast response and then the impact comes, and then so that it's how do you couple those two responses. So you can already start imagining all the challenges that are involved in that field. Explosive, then the blast wave is a shock wave expanding from the center of the explosion. So if you look at, I think I may have it on the slide next, we'll talk about that. So so there are either let's say homemade, so categories of explosives. So either homemade, so in this case these are, for example, ANFO is homemade, and obviously they will be limited. The Oklahoma bombing, I believe you saw this is I showed you a picture of it. This was homemade and we saw the amount, but again that is not purely because of a blast, it's part of it, and then there's progressive collapse involved also. And then of course then you have military grade, and even in military grade you have a couple of different varieties. You have low explosives and high explosives. So we call this LE and HE. Then even here there are two types of explosion. This is an explosive, but when you look at the explosion itself, one is what is a deflagration, and deflagration, this is in this case, so what happens is when you are mixing these two, there is detonation, right. So and there is a rate of detonation, it's a chemical reaction. So in a deflagration, the rate of detonation is lower than, and the velocities, the speed at, when I say rate, the speed at which is lower than the speed of sound. And then you have the LEs. In this case, this is a little bit higher, so there is a rapid burning and of course flames that are involved, and sometimes it's difficult to put a number to it. It's often a range that is specified, whereas HEs, they cause what is known as a shock wave. So you can see that when you have burning, then pressure builds up and goes down. So the time over which it occurs is much larger, right? Whereas when you do HEs, the time at which the detonation occurs is extremely high. So that is the difference between what is categorized as HEs and LEs. To look at it, shock waves, they travel at speeds greater than the speed of sound. And in all this, you have, as we talked about, something called a detonation velocity. So this is basically the speed of, this is within the explosive itself, the speed of the detonation wave through the detonation material. So when they talk of detonation velocity, keep in mind, again in a design we are not going to consider this as a specific criteria, but just to have an overall idea about it. And this can be from 5,000 to 8,000 meters per second. So HEs in particular, they cause heat, a lot of heat, then of course a large amount of energy, and it also creates strong blast waves. So we'll go a little bit more into it now that we have an idea what they are. HEs, high explosives, are bombs, mortar shells, even bullets, for example, are considered. Again, that's not a topic that we will consider. Professor Agappan is doing a lot of research in that area. He's done a lot of research in that area. If you're interested, please contact him. You'll have some great opportunities to work in that. Uncased, so there is what is known as cased, these are all terms, or uncased charges. Or explosives, and both are quite different when you design for it. The uncased explosives are used now. A lot of companies do demolitions. Demolitions, what do they use? TNT, right? That's more of a implosion, not an explosion. So there, its principles are similar, but it is to create localized failures of connections such that materials, everything starts imploding. So that's a really extreme case of, I guess, a specialized case of what we are learning out here. But again, principles are similar there also. And TNT, you will hear, this is the most common explosive. There are lots of others as well, but you will see soon that this is sort of the baseline. So baseline explosive that is considered. And this, I said, in mining construction, this is used This is again either you can call it commercial or even sometimes home. The one in Oklahoma was homemade completely in a truck. Now, low explosives include products like propellants, propane cylinders, liquid fuel, gasoline explosions could be considered, natural gas explosions. They're all, it takes time again for the peak pressures to develop. So, time is what we get out of this is time of pressure is an important component. Unlike any other type of loading. In fact, some of the principles, it's just from this course, even if you don't apply or don't become work in this area, it's just fascinating to see how structural behavior is from this side. As we will go through, there are, I find that quite exciting. Just to, I was never exposed to those kinds of behaviors and those kinds of concepts in either my graduate or PhD or even undergraduate. It's hard to cover those things in a curriculum. So those things expect in the next few days. High explosives, again we talked a little bit more about it. Release energy by detonation. Just to give you an idea, the energy, for example, let's say Q, let's call it Q, this is the specific energy. When we say specific energy, then this is in kilojoules per kilogram of the explosive. So for TNT, it is approximately, and it's hard to put a number to it, let's say approximately 4500 kilojoules per kilogram. Then there are others. For example, there is an explosive, in this case this is higher, 6400 approximately kilojoules per kilogram. There is another explosive called RDX. Again, don't ask me who uses what, under what circumstances and why they use it, but I go by what's there in literature for different types. So if you are asked to design against those, or then knowing these numbers or finding a table from your sources of what they are is important. Then the detonation is of a very short duration. We are talking of the order of milliseconds. So we are talking of the order of not a few milliseconds, maybe 5 to 100 or so, maybe a little bit more, but we are definitely even not talking of 1 millisecond out here. I mean, not even 1 second, I should say, about 0.1, maybe 0.2 seconds. Even then, it starts, things drop very rapidly. And you'll see that that is a important consideration. I mean, when we start looking at focusing, for me as an engineer, numbers are, and for all of us, right? Without units, number one, and the numbers associated with a unit, it opens your eyes to a lot of phenomenon. We are working on a multi-physics problem where the response is of different time scales, all in the same environment. So we are not just talking of length, time scales, materials are different, all of them in one, right? So those complexities come into play. Rate of this is not very important. The rate of detonation not dependent on the particle size. It does have a high shattering effect. Now main thing is, you see release of energy by detonation, release of energy by rapid burning. That's one of the big difference. So it depends on the amount of oxygen available for that burning. Much longer time, so could be of the order of seconds. So your pressures that is generated, now you have to apply it over a longer period, even 10 seconds, 20 seconds. Then you will see later on how that plays into the response of the structure. There are some really fascinating aspects on this course, especially in the first few, that I think I'm pretty excited to present, and you'll be excited to learn about them also. Grain size is important. Again, that is within the detonation or the explosions itself, and it has much less of a shattering. This is prolonged exposure to load. Not exactly wind, but certainly something like wind. Pressures are very, very high. For example, let me talk, I'm thinking in terms of PSI and not MPa. But let's talk of the order. Let's say you're designing this building, right, this room, classroom, for a certain load. If you were designing, let's say, the wall of this for a blast load, what is the ratio of the pressure difference? Just the magnitude of the pressure difference, you think? Bridges fully loaded with trucks back to back. You start calculating, they'll be of the order of even less than 1 psi. For example, we design high loads are 200 pounds per square foot. Let's put it at 144 pounds per square foot. How much psi? 1 psi, right? So, but here, what is tire pressures? Maybe you can say it in MPa. Do you have any idea of how much? Have you filled air in your tires? Huh? 30, how much? 33 psi. What is the load on a building? 1, less than 1. So look at the difference in, and that explodes out, right? So start thinking in terms of that shift, in terms of scaling. High explosives that detonate to create shock, they shatter. Low explosives, I said, again low in energy, lower pressure, longer duration. So for example, if I were to plot these two, pressure versus time, maybe I should have plotted in the same, or I can still plot in the same. So this would be more like this, where this is HE, whereas this would be LE. So you see the areas could be same. This is the area under here. The area, but the peak, there are 3 variables involved, and we'll talk of all those. One is dependent, of course, and so how that affects the response, those are the things that we will be covering. So what happens, what does happen physically, what happens in an explosion? Let's say you have a TNT explosion here. So instantly it gives rise to a compression wave in the main explosion. So there's going to be, just like sound, right? Sound travels, I'm giving a compression here, and it travels to you in the form of those sound waves. So in a similar way, there is instant compression, and not only that, there is gases also involved. I am not pushing out so much, I'm just pushing out a sound wave, but here you have gases that are expanding with high velocity, pressure and temperature. So this results in a shock wave. So instant rise is the shock wave. It propagates through air, results in the sharp discontinuities. So when you saw the picture, you saw it goes and instantly comes. Those discontinuities, and then that's the positive phase, is where the pressure, so you actually have your atmospheric pressure, and this one rises above the atmospheric pressure. And the positive phase, if this is the time So there is also actually, if I were to take away the atmospheric pressure, you will have, so this is considered the positive phase. Now associated with the shock wave, there is also wind particles. So that is moving with a certain velocity. Now that, just like you have your wind moving, your normal wind forces, same way each pressure range there is a wind velocity and pressure associated, which causes a dynamic pressure. So you are already now talking of two types of pressures. An incident, will call that the compression wave, it causes an incident pressure. We will be talking of a couple more terms later on. And then you also have a dynamic pressure on the objects just because of the speed of the wind, and it is clearly much more intense compared to your regular wind. This is something I don't really focus on, but just for you to know, you have different types of chemicals, primers and boosters, so we'll not spend time on that. So I think we have talked about this, but let me just give you a little, I wanted to put this as a review, so to speak. So with the booster you have a compression wave. The compression wave, we've seen it goes much faster than the speed of sound. Then if the compression is sufficient chemical, again the initiation of the chemical reaction will occur due to elevated pressure and temperature conditions. So we know those are needed for, again, chemical reactions to take place. That's one way. And the reaction is very rapid, which causes a detonation wave. Then the detonation wave goes through the material itself in excess of the speed of sound, depending on what type of explosive material you are using. We have looked at 2 or 3 different names. We haven't looked at them in details. Then that wave from the material reaches the interface between the explosive and air. So that's where the gases then they expand with high velocity, pressure and temperature, and the boundary between the hot compressed gases and air is defined. Then behind this boundary, pressure and velocity sharply decrease after it passes through. So this is your explosion, let us say this is your boundary, and then the wave goes, and then after it propagates in this region, it drops down very quickly. So this is the shock wave, and there is a discontinuity associated with the rise in pressure propagating. Don't ask me too many questions on this. I might not have an answer, but you understand the basic process, right? At least aware of it. So shock waves are large amplitude pressure waves produced by an explosion and faster than the speed of sound. A blast wave, this is the dynamic, again some of these are just to review. In these explosions, large amounts of shock wave passes outward from the core in a few milliseconds. What are the magnitudes of pressure that is generated? What are we talking about in this case? So it generates, you see this is extremely high. Gas pressures can go 10 to 30, not just megapascals but gigapascals, but luckily by the time it arrives, goes outside into the air and comes into the structure, it falls down into megapascals, but they are very, very high. So I think most of it we have covered. We can move forward. If one, I'll give you all of this, you can read through it carefully, but I don't see anything new in this. And okay, once again reviewing the 2 things we have talked about terms wise. We've talked of a deflagration. this is again in low explosives. Basically this occurs, and if you look at it, this is the pressure time deflagration, and these could be of the order of 0 to 10 psi peak pressure. Whereas here detonation, so this part is the detonation, this can be of the order of about 50 to, I mean in our experiments we almost went even more, 100 psi, and what 1 ksi is about 7 megapascals, right. So you can imagine this is 0.7 megapascals or half of it. Explosion that produces high intensity shock waves, velocities, this is something we calculate. In fact, it is, we'll see later on in buildings, it is important to, the detonation velocity itself is not important, but the velocity of propagation can be important. And note some numbers. This is at 6,000. So when you get some when you do calculations, you're asked to, nobody is giving you answers, especially in this field. In a lot of other books, you can turn the page and you can find an answer in the back and feel good that you've done it right. But in this field, there are no answers. It's only you have to gauge yourself. So how do you know you're right, or at least by being in the ballpark? Looking at numbers and units. So that's why I'm highlighting some of them. So this is, I don't know if this is with the WBDG changing in, actually changed in October of 24. So I don't know if this picture is still there, but look at how, what are all the important components. So here is the explosion, that is your standoff distance. Don't worry about the term hemispherical, we will talk about that, we're coming to that soon. So there is the wave that is impacting, say this is your R, and the magnitude of it changes, decreases as you go outward. That's why the intensity is peak out here, and as you go outward, intensity reduces. So there are two terms here. One is overpressure. Why is it called overpressure? You should. Over atmospheric pressure. So as it propagates through air, it is overpressure. Now think of, let's say this building, say this is a building and this is another building, right? Both are impacted by the same blast wave. What happens to this building? It will go deflect quite a bit, right? What is this building doing? It's standing. Now which will experience more pressure? A, B. Which question is, which experiences more pressure? A or B? Huh? Explosion is here. B, right? Something like this. You're pushing somebody, right? The person doesn't resist. Am I feeling any pressure as you push? I don't feel any pressure. I'm just moving with it, right? But if I start pushing, right, more resistance I apply, I feel more, I can start feeling same thing. That effect in a building is called reflected pressure. So if you're over pressure, it's called PSO, or this is PR. Reflected pressure can be much more than over pressure. Orders high, not just 1.2, 1.3, it could be 5, 6, whatever the case may be. So in the front face, this is the front face. and we will do examples of all this, you see that you have overpressure, and so you have PR. PSO is in air, but reflected pressure is in the front. Now on this side, then there is these structures. Actually, if you take a circular structure versus a rectangular structure, and then there is blast and this is blast. Now this tends to reflect back. This is PR. Now here there is diffraction. We don't need to specifically go into it, but the behavior is going to be very different. So that's why it is recommended. It's sometimes hard to predict what happens due to diffraction aspects of it. So here, now notice everywhere it is into the structure, and these are just over pressures. We called it PSO. This is PSO. This is PSO. This in the back wall is PSO. So only the front face is experiencing. So when you are designing anything, and this applies any mechanical structure, whether you are working on take a structure, imagine any structure you are wanting to resist these effects. So you should recognize, that's why you analyze for your bomb effects to be in different locations, because you want to protect everywhere, right? Like let's say it's an armored vehicle, then you want to know where it is, then you analyze, but recognize that depending on where it is, you have reflected and side on. Okay, is that distinction clear? What? Oh, what's the difference between the two? So overpressure, let's say this is the structure, right? Detonation is just, so up to here it is overpressure. Then once it hits the building, right, there is reflection. So the building is moving because of, if it is not stiff, less reflected pressure. If it is very stiff, but you will see that it doesn't, when we calculate it, it doesn't depend on the stiffness of the building. We will assume it to be rigid structure. So that is what is reflected. Take the example, right, of resisting versus not resisting. If you don't resist what I do, you don't feel, your pressure is translated into velocity or movement, but here movement is restricted. So like oak tree versus you have palm tree, for example. Palm trees are small, thin, tall. They'll really go down, but they come back up after the wind occurs. If you take a big oak tree, what's going to happen? It's just going to topple. So what are we talking about numbers wise? So here, for example, 1 kg of TNT up to, this is in what is known as the nearest near range. So you're talking of 1 to 1.5 megapascals, and you can convert that to PSI as well. The UFCs are on PSIs. Then you go further along. So this is R1, then this is R2. If you go further along, then up to 0.1, say 0.3 megapascals inside can injure lungs. So and going further down, or even here 0.1 megapascals, your eardrums rupture. So those are some of the ranges, and then you go further away, R3. So here you have, this is 0.01 megapascals. So in this case rules out fatalities, minor injuries may occur, but of course this is fragmentation, that's a different issue. So just to give some numbers to keep in mind, this is important especially if you are designing against, right, to protect. So there is designing to prevent or to, again, levels of protection, but when you come to levels of higher levels of protection, contents inside are human beings and you want to protect ears, what should you reduce it to? You reduce it, this gives you some ideas of the actual numbers. So as you go along this course, keep an idea, these are the things more than will, as Professor Aragappan said, will provide you these, but if you're taking notes, I would take notes on the numbers, right, those are more important. Here is an interesting, and should also mention that 12:45, no? Huh? No, what, it goes till? 12:43. Okay. We're going to be way behind, but that's okay. We'll go as we, yeah. So you have here blast injuries. They are primary, secondary, tertiary, and quaternary, fourth. So this is, primary is direct impact, secondary is the fragmentation plus direct impact, then tertiary is this thing hit by surrounding objects. So that's why when you design it, all these things are, for example, glass, that would be, this is glass breakage. And then quaternary, these are from inhalation, these are biological effects. So when you're looking at protection, you have to present a comprehensive package. So as you're seeing, the picture is already broadened. What is surrounding? What is my glass type? All these, it's not just structure alone. So this is again from the UFC 340. We'll get familiar with this. So here you see, this is your explosion. At a height, this is the ground. Now what you have here, this is the, it's also called the incident wave. This is the first shock wave. And then of course the angle of incidence we talked about. Then what happens is, the incident wave is coming, it comes here, and then what happens at the ground? Ground reflection, right? What does speed of sound or speed of a wave depend on? Yeah, medium. In terms of medium, what metric? The density, right? So air has a certain density. The same thing even in seismic principles too. If you have a soft soil, your seismic wave speeds change rapidly, right? Same principle here. When it hits the ground, reflects with much higher intensity. So there is transmission to, well, that's another thing. It's called cratering. So cratering is something that occurs, it affects the foundations of the structures. So that topic is a separate topic by itself. What are cratering? You can have a whole lecture on just cratering alone. Again, those are all best estimates. So what you see out here is already, so these are reflected waves. So pay attention to, this is in dashed lines. Now what's going to happen when two waves interact? There is, so as these waves interact, this is, the interaction itself causes a third wave, right? So two rivers join, they actually, I used to wonder, two rivers join and then another goes, and they used to say there are three rivers there. I said, why? I see only two. But this will have name A, name B, name C. So similar to that, the effect is two pressures, the third pressure is, so this is, that's why it's called the triple point. The path of the triple point is, and this height is called the Mach. So this phenomenon is studied, again, explosions, explosive engineering is, you should, if you are interested, you should spend some time, look into it. It was studied as, I mean, these were proposed over 100 years ago. Many of what we use, equations, are perhaps over 100 years ago, if not more. And again, I was talking to Professor Aragappan, he was talking of the basic mechanics of understanding the fundamentals of those itself, because they haven't been studied a whole lot, these topics. So that's what is called as a Mach front, and it depends on where the building is. It hits the structure. Fortunately, we are not going to be looking at some of these things. If you are doing advanced modeling techniques like finite elements, then you have to start considering, depending on the type of modeling you use, reflecting boundary conditions versus non-reflecting boundary conditions and things like that come into play. But for this course, you really don't need to worry, but you should definitely know these terms, the Mach front and the triple point. The whole idea, it is difficult to design, but let's say an ideal goal is to design a structure to avoid the Mach stem. So the Mach front or the Mach stem, they're about the same thing, and this is actually also called the Mach reflection. The reflection that you see, it is basically, it is a much higher over pressure, and that's why better to avoid. So how many types of pressures we've talked about so far? Over pressure and reflected. So two main pressures to keep in mind.
Is there any given this standard for this height of the
There are, but I'm not covering it here. Yeah. So and that's why curved shapes, they actually reflect. Convex shapes we suggested, they reflect much better, but piers and columns, there is reflection and diffraction involved, but anyway, those are part of regular designs. So boy, I seem to be talking a little ahead of the slides. Anyway, it's good to review. So the Mach stem formation occurs when a blast wave reflects off the ground and reflection catches up with the original shock front, creating a high pressure zone. Anything in this area experiences peak pressures that are several times the peak, that's why to avoid, of the original shock front. So if you have your side on pressure, this can be much higher. So, a structure, and that leads up to your question, if you can calculate, maybe I think that's something this course has evolved, maybe next time I should include some, I am not prepared for those calculations, but I think that may be a good example to add in the future. If the height of the triple point exceeds the structure height. So we've seen three things, right? Negative pressures also, because there's suction behind. So those are the positive phase. Then you have the negative phase, and we'll go through all of this. And then we've also talked about the dynamic pressure, the pressure due to wind velocity associated with the blast wave. We'll see how to calculate all of these. So again, your wind speed you calculate based on your wind pressure is calculated based on the speed, wind speeds, right? That's what this corresponds to, the particle velocities. What is your overpressure and particle velocities? So if you want, can be used but we will do so failure over pressures for buildings. This is again published paper. This I should perhaps have the full reference. So it gives you over pressures in PSI. So keep in mind 1 KSI is about 7 MPa. So if we think in terms of the units, right, that makes more sense. So 1 PSI is how many? 0.007 MPa or 7 kilopascals. So just to give an idea, single story framed residences with or without basements, over pressures of 3 roof collapses, then 2 or 3 story masonry load bearing walls, over pressure of 4 roof collapse. Again, roof, know what kind of pressures are acting. Store fronts, multi-story, somebody was talking about steel buildings application. There you need about 10 psi to 6 point, and there is also the time effect. We will, that doesn't, this table doesn't speak to it. Then multi-story reinforced concrete frames. So this is in reinforced concrete, again 10 to 6, and the definitions are there. So all of this, you see, they start failing around 10 psi or so, and this impulse is also another part of it, but you can look up that reference. And we also looked at some probability of survivals. We've not looked at the probability, but we've looked at pressures that cause that. So you see that 5 to 11, you see if you can drop that pressure by half. Here drop, you design to drop pressure in half, probability goes up 9x. So now hopefully that hits across why the standoff distance is very important. So let me stop this. I think since we'll probably finish 12:45 or a little bit maybe, but we'll continue the lecture part of it also in the second. Is that fine? Yeah. Especially example. Okay. So let me quickly take a moment to export this file. Meanwhile, if you have any questions, feel free to ask. If if I don't save it now, what happens is these are stored as image files, JPG files, and this is best to convert it to a combined PDF, otherwise later it becomes a challenge, especially large ones. Okay. So, we talked of risk assessment and if you look here, there are variety of things. One is I will talk about the UFC, then there is ASCE 59, and then there are others as well, and perhaps we have to do we might, I think, combine my solution and your solutions in the tutorial session this afternoon, which should work. That may be actually a better way, because you will see what I am doing and then you can see yourself. So, briefly about okay. Little bit introductions again. Initially, now you see this is probably the first time, right, a course like this is, or very few courses like this are offered. So, when we talk of the past, we are just talking of recent past. Even there, not many people, some of the students I have taught there are now working exclusively on these areas, and some of them are not even civil background, they have mechanical backgrounds, they have come and they work for companies that do nothing but protective designs. Specialized companies do that. So you should get hopefully a lot of fundamentals, although we focus on civil. So it is becoming required. I do not know how prevalent it is in India, but structures should be considered if depending on its importance. Expertise are needed when you have irregular and non-building structures. Again, large bombs at small standoff distances, effects other than air blast are significant. So what we are leading up to is risk assessment, and there is a standard as well. This afternoon session I will bring that document. So the risk assessment, so some fundamentals of risk. What are some common definitions? Again, you do not need to take down notes, we are going to give you all of this. Risk is basically, now this is, you have an unwanted event which may or may not occur, right. So you are designing for that. So fundamentals of a risk assessment is there are three things. One is that event has a cause. The cause is hazard analysis, right. You come up, you have to quantify it. The cause is quantified through hazard analysis. Based on probability of the unwanted event, again, which may or may not occur, you have a threat. So you do a threat analysis, hazard analysis, you have a threat analysis, and then the expectation value of an unwanted event you calculate, that is what you define as a risk. Now what is acceptable and not acceptable risks? Those are dependent on your experience, your organization, your client. So this is basically the definitions. So what are the basic components? It is again, keep in mind, it is a subjective procedure. I myself am aware of at least 4 different ways to calculate risk, and the threats of course only one definition at the end of the day for our purposes, but each, for example, emergency management, I mean you are doing risk against cyclones, that procedure could be very different from risk against explosions. So it depends on what your organization takes time to develop and come up with. So but the fundamentals are, you have a consequence analysis and you calculate a value for C. Then you have a threat analysis. This is first, this is second, a threat analysis This is the likelihood of a attack. Consequence is you are calculating the pressures and time. That's a consequence, right? Threat is, it depends on type of structure, where it is located, importance, all those things. That is how you define a threat. And then finally, this is from the perspective of the structure. You have a vulnerability analysis. It's often called a CTV analysis. Countermeasures in mitigating an attack. Then there is individual. It's presented in this document 4-420-02. So then you have a risk which is nothing but can be defined as a product of CT and V. So there are very different methodologies depending on the type of building and who owns it. Defense or Veteran Affairs, Homeland Security, they have, and we won't go through all of it. We will go through one of them. Building codes, here you have goal is life safety. You address usual occasional hazards, you have a return period, and basic loads are dead, live, wind, snow, earthquake. You can have hydrostatics, whatever you want, you are all familiar with it. And it is prescriptive. For example, ASCE 7-22 or ASCE 7, whatever year you use, it is the word is standard, and it also includes minimum standard. It's not just a standard, I should say minimum standard. It's up to the engineer to use higher than that. So it's prescriptive. Dead loads are 100 PS, whatever, you know that for sure. But in security criteria, goal is not, if you observe the differences, life safety, here is protection. Humans are also considered assets. So protection, address international hazards, and risk is based on loads and resistance. So this is prescriptive loads, prescriptive resistance. Here it is based on risk. So it is risk based, whereas this is, so note the difference between the two. So what are some of the things in a consequence analysis? Things you consider are assets, owners, assets, as I said, property, people. Information is also an asset, like law libraries or data centers now. So especially now, what, I don't know how prevalent data centers are here, you can see that companies, you could convince a company to, let's say Google or somebody like that, to say data centers need to be protected against blast, right? It now becomes now data centers are not part of many of these documents. This thought only occurred to me recently. Even they may not be aware that you could need to be protected, because that's the only, of course you have redundancies, but then still you can consider that to be a potential for applications. So up to the engineer to tell the owner who possesses control or controls the assets. Owner is different from a user. Who are the people who are actually using that particular building? Then what is the mission, purpose or function, and then what is the undesired event? You have to define all of this as part of the consequence analysis. Loss or compromise of a specific asset, and then the consequence is defined as the impact of an undesired event on owners and users. Loss of a data center, what does it mean to the user? User loses the life of user of the building, whereas the owner loses value, property. They are two different losses. Then in each asset you identify and prioritize mission of owners, identify and categorize the asset, determine the impact of the asset loss on identified missions, then the time required to replace asset if lost, and then you calculate all this, and then you calculate a consequence factor C, and we will go through an example here. So, a consequence analysis, this is one example, it is a very basic example. Again, it depends, very subjective. If you were using a simple example, you define, for example, criticality, the 4 things that we talked about in the previous slide, criticality to the owner, and you can calculate it from this equation. So, it is the owner's estimated remaining mission capability. Then the second thing is criticality to the users, again similar equation, again users, it is from a user's perspective. Then the time to replace, and where TR is, for example, a data center could take a year to replace, build again and everything, and the days to replace versus a high value which is 180 days. Now you might change that, you might say a high value could be even lower. So, you can even, this the word keyword here is usually. So, the relative value for the owner again is calculated from that. Then we come to the threat, and second part of it is a threat analysis. A threat has a hazard, attack, aggressor. We will talk of some of these things even in terms of UFC has all these tables. Tactics and tools. So, a hazard is the potential initiator of an undesired event, this is the explosive. The attack is the attempt to initiate it, then the aggressor is the person, depending on who it is. For example, it could be a terrorist activity, it could be accidental. If you see in terms of protective structures for petrochemicals, that is accidental explosions. You won't call this intentional explosions, this is accidental. So, here you see they use the word intentional hazard. Then what are all the tools? For example, cars or walk, whatever they have capabilities in terms, and the threat is the likelihood that the specific type of attack will occur during the planned service life of an asset. So, in the intentional hazards, you identify the aggressors, tactics and tools, whether they have been past attacks, determine it would be consistent with the objectives, aggressors' objectives whom you consider to protect against are important. You won't protect against all aggressors. What's the worst aggressor you want to protect against? And then you assign a threat factor. So, here again, as you see, it's so subjective. It's just some numbers 0.2, 0.4, 0.6 and 0.8 based on what you see and very high. And then the threat analysis for usual and occasional hazards, again this is just a comparative slide. If it is a return period, it is 0.2 in 50 years, if it is low, 0.4 in 50 years with 1% annual return. Floods, medium 0.6, this is for usual and occasional hazards, that is intentional hazards. So, risk analysis is done even for normal threats as well. And then you do the vulnerability analysis, physical protection systems, combination of elements intended to prevent an attack, and vulnerability is the likelihood of a specific type of attack, if it occurs, will actually result in the undesired effect, that the asset will fail or PPS will be unsuccessful. So based on this, you calculate a vulnerability factor for, if it is for occasional hazards versus, and we are working with and so if you see, that is within the structure itself. So depending, it's equivalent to the level of protection, so to speak, for that element. But based on that, you can come up with numbers, and these will be provided for you. Goes from 0.05 to high, and then for non-structural intentional hazards, this is non-structural elements. There are quite a few water tanks on top of a building, for example. You have some calculations here. Then you calculate based on, if you go through very detailed, we will go through a detailed example also, but you actually create a diagram for each asset and identify the vulnerable attack paths. You estimate detection probabilities and delay times using tables, and then you are using methods to calculate the probability of the attack. But here you can use these numbers. You can use these tables based on judgment from very low to very high. So we saw that risk is a combination of C, T and V, and the product is the risk. And then based on this, then you can this is the risk itself, whether it is very low to high based on CTV products. Whatever you get, you use this table to calculate the risk for that structure. So this is a basic understanding, and you can try. The numbers of risk you get from different methods are different. That's why it's important to have a background of using a method and what an acceptable risk is. So let me save this. We'll do one more and then we'll break for lunch. So the risk is assessed using a document called UFC 4-020-01, and there is a whole form for that. And here you can take some notes, but as you see, this outlines. I've just taken the steps part of it and then giving you the process. So there are several steps, and you will be going through an example maybe today. Convene the planning team. Step 1, identifying the assets, then determining what is to be protected, determine the asset value, then determine the aggressor likelihoods. Each one has a number associated with it. Identify likely tactics and threat severity, then consolidate into a design basis threat, Then you determine the levels of protection that you need. This is from the user or the owner, and determine the planning risk level. There are all equations associated with that. So, here you do not have to copy down. We will go through. I think we can do our example and let them do also at the same time, or that may be good, right? Okay. In the tutorial we will go through this. Identify assets. So, there is a section based on the facilities. This is just to highlight all the types of facilities that are there in table 3.1. What are all the assets they are assigned? This is table 3.2. Then the asset value is another section. There are up to 5 ratings that are based from table 3.3 to 3.8. Then you sum the rating factors and then you determine what is known as the AVR. Now, if AVR apply only, then step 3, if AVR is greater than 0.5. So, if you get it more than 0.5, then you proceed. You take aggressors from table 3.9, likelihood factors again 310 to 323. Then you sum the likelihood rating factors and aggressor, then determine the aggressor likelihood rating factors. Then section 3.7, you identify the tactics and threat severity levels. Again, these are the tables, the potential tactics based on the asset. Select applicable tactics based on the aggressor. Then applicable tactic threat severity levels. And I have not shown you these tables, so you might be in the dark right now, but we will be going through all of it. Then all of it you consolidate into an initial. This is where the whole purpose of doing is to define our DBT, and you can change based on that. There are a few categories. Then you determine the levels of protection again from the user or the owner desired. Then based you calculate the planning risk levels. There is an equation for threat effectiveness rating. Then the PI initial protection factor, this is P sub I for the target LOP, there is a table for that, and then you adjust, and then based on that you calculate all of this is PI. So, there is an equation here, it is a simple equation, all of these. Then you calculate the risk level. Then you assess the acceptability of risk levels and identify user constraints and incorporate design requirements into planning documents. So, it is a fairly, as you see, very detailed process. And one more thing, I just want to show you and then we will be done, or maybe I will do one thing. It's just so once we have done all of this, so these are all different tables. Oh, so this is what the vulnerability part of it. This is the equation that I wanted to show you. You get your TEH depending on the types of aggressors, and then your PI average that you have calculated, the initial protection factors, level of protection, and then based on that the risk is calculated using this second equation. This is the average value AV TLH. This is basically the vulnerability part of it. Oh, I didn't know this can move. This is vulnerability. So, risk is relative. So, if you are looking at your neighbor's answer, it might be way different and both could be wrong, all right. Okay, I think we can do the example in the afternoon, right? Okay. So we'll break for lunch, and they've been told no where to meet for afternoon.
Yeah.
Okay.
So afternoon session, what we do is we meet in BSB, Building Sciences Block. It's the Civil Engineering Department building, second floor. So there is a Department Computing Facility, DCF. So we'll all meet there because there are systems available, so that you can come there, sit, because you can see there are a lot of tables involved, right? So Professor Ganesh will be parallelly working an example problem. He'll also give you another example problem, so that you can parallelly work with it. So there is enough space there also. Okay. So is everyone clear with the location? BSB, Building Sciences Block, which is two buildings next to this. Okay. And it's in second floor, Department Computing Facility. So that's where we need to come. So we'll organize there. Tutorial session always we will have it there, unless otherwise it's stated. Okay, I think we can leave for lunch, so we'll meet there.
So the file is stored in Scribble, day 1, session 1,